Hi everyone, welcome to the 19th lecture of CS287, Fall 2019. Today we're going to mostly cover off-policy model-free methods. But before that, a couple of logistics. So we've announced a few important things on Piazza, but I also want to announce them in class. One, the exam for the class has a handout with the questions and the answers. So there should be zero question ambiguity when you come to the exam, because you've seen the questions before, you've seen the answers before, but these are the things that we think are the most important things for you to really know. It's about 20 pages. The handout is almost complete. We're going to add a few things we covered in today's lecture and add a few things we cover in Thursday's lecture. But other than that, the handout is complete. And so we post that on Piazza. Please study that. The questions will come literally from the handout, and the answers will be expected to be literally what's on that handout. And it's all things we covered in class, but it's laid out a little more kind of specifically in the handout in a way that you have question answer specifically for you to study. The timing of the exam will be next week, Thursday evening for most of you. There are a few of you who have conflicts, and Laura's sorting out a resolution for that. If you haven't sorted it out, make sure to do it really soon, because after tonight, probably it's too late. So contact Laura as soon as possible to resolve if you have a conflict. Any questions about the exam? All right. Then let's get started with lecture for today. Today, most of what we're going to do is off-policy methods, but I want to first recap what we covered last lecture, which is policy gradients. And there's a part we didn't cover yet that's actually really important in policy gradients, which is the trust region aspects to make sure you can optimize in a much more efficient way than if you just do gradient steps. So let's start with that, and then we'll switch to the off-policy methods. Not what I wanted. So, as a quick recap, in policy gradient methods, the likelihood ratio policy gradient, what we do is we essentially optimize our distribution over trajectories. And so when we take the derivative of the objective, really what we're doing is we're shifting the probability mass onto trajectories that are higher reward and away from trajectories that are lower reward. As we work through that, we came at the following gradient update, which is we sum over all trajectories we collected. We sum over all times in those trajectories. And we look at the grad respect to theta, which is the policy parameterization, log pi theta action we took at time t in trajectory I. Or we've been writing u, so let's write u. Action we took at time t in trajectory I, given we're in state st in trajectory I at time t, and then we would multiply this with the sum k from that time till the end of reward we obtained in states sk taking action uk in trajectory I, and then we subtract out so the summation is this part, and then we subtract out a baseline to reduce the variance, and the natural baseline is to subtract out your estimate of the value function. So we are estimating a value function at the same time, which may be parameterized by v phi for state st in trajectory I. There we go. So that's our policy gradient update equation. If you want to put this into, let's say, a TensorFlow, PyTorch, or other automatic differentiation framework, it's actually very easy. You can just provide as your objective just forget about this part. If you remove that grad part, you have an objective you can optimize. You can say maximize over theta, this thing over here, and then you ask for it to optimize, and then it'll compute the gradient for you, and it'll take some steps for you, and then at some point you say enough steps because this is only locally valid. You're not going to let it run till convergence. And then you collect more trajectories. For the new set of trajectories, you do the same thing again over and over. And in parallel, you fit your v phi. So your v phi of S Ti is fitted to your empirical estimate is typical. So it would be fitted to sum over, in fact, the thing that's shown there, k equal t to h, r ski UKI, and you minimize this squared error, or maybe a Huber loss if you don't want to pay too much attention to the big errors. Minimize this over phi, sum over all I and t, and that gives you an updated v phi, but maybe you want to do a small number of steps because, again, it's just current data, and you don't want to overfit to the current data. So probably you don't fully minimize. You just have an objective, run a few steps, and that's your updated v phi. So that's really all you have to do to run a policy gradient method. And of course, there's the rollouts that happen under the policy pi theta. Now, what we haven't looked at yet is what we've seen in the past in optimization matters a lot is the step size. If you optimize this objective, how far do you want to step when you take a gradient step, or how long are you willing to optimize this objective if you're just running an optimization directly on this surrogate loss? Called surrogate loss because not the real loss. The real loss is the expected rewards under the policy, and this is just a proxy that we think is reasonable locally. And so how local is that? Is it extremely local? In certain directions, you can go maybe further than other directions, and that's what we want to address now. Any questions about this? Because that's what we'll be building up upon for the first 20 minutes in this lecture. Okay, and then maybe one extra thing that's worth noting, we saw an alternative derivation of the policy gradient where we saw that instead of having this as our objective here, we could also have instead this ratio, importance ratio, pi theta over pi theta old. And the gradient of this thing is the same thing as the gradient of when we put the log in there. They have the same gradient, locally they're the same. But in fact, even though the log is common in policy gradient derivation, people focus on the policy gradient, what we're going to start looking at now, which is trust region methods, this objective is a somewhat closer local fit than the one with the log. And so if you're actually going to optimize the surrogate loss, most often this gets used as a surrogate loss rather than putting the log there. And we'll see that happen in what we cover today. All right, let's So the first thing we're going to cover is trust region policy optimization, which was the first method to successfully optimize large neural network policies a reinforcement method to optimize large neural network policies to learn to control simulated robots. And then we'll see a kind of new version of that, PPO, which is more often used these days, that can be understood very directly once you understand TRPO. So, step sizing and trust regions. Step sizing is necessary as gradient is only a first order approximation. Terrible step sizes are always an issue, but how about just not so great step sizes? What happens? Well, in supervised learning, let's say if a not so great step size is step too far, well, you'll look at the next batch of data, it'll bring you back in the other direction, and it essentially self-corrects. you might have wasted a little bit of time, but it self-corrects for it. In reinforcement learning, what happens? You step too far, you have a terrible policy. There's no data waiting for you. That terrible policy is the thing that's going to collect the data that you're going to use for the next step. Okay, well, that next bit batch will be corrected under this terrible policy, and it's not really clear how to recover because that terrible policy might just get 0 reward, a very negative reward, and not give you much signal in its rollouts. And so the only thing you can do then is just say, hey, maybe go back to what I had before or shrink my step size and hope that this time it'll work better. So no automatic self-correction happening in RL because you collect the data under the policy that you're learning. Now, you can say, okay, what can we do? The simplest thing would be essentially line search in the direction of the gradient. It's very simple. You have a gradient direction, you line search in that direction, you see which is the optimal step. For every step size, you can do a bunch of rollouts, measure the performance, and see which one is best. It's simple, but it's also expensive. For every evaluation on the line, you have to do a lot of work. Let me give you a little bit of extra color. When we were covering optimization methods earlier on, we also had line searches. But very often in those line searches, when you're doing, let's say, convex optimization, there are little tricks you can play that makes your line search much, much cheaper than evaluating the original objective. You have some shortcuts that make it cheaper. But here, you just have to do a full evaluation, and so it's as expensive as evaluating your objective to do a line search, and you have to do it multiple times, so not great. It's also naive, because it ignores that maybe your linear approximation in some directions is better than other directions. And so maybe in some directions you can trust it more and go further, other directions you cannot. So what can we do that's more advanced? We can have trust regions. Trust region tries to spell out where the approximation given by the gradient is good, and that region is called the trust region. We've actually seen this a little bit before when we were covering the penalty method for constraint optimization. In the inner loop of our preferred method, we had a trust region, a very simple trust region. We're just a quadratic trust region, hard-coded to be staying within an epsilon ball. But now we want to see if we can do better. We're actually seeing something that does a little better. When you do second-order methods with a Hessian, let's say, effectively you have a Hessian defining your trust region, and we're going to try to do something similar here. Once you have a trust region, you can solve for the best point within the trust region. So imagine you have your gradient, which defines your first-order objective. Then if you had a trust region, in this case we're going to define it by the KL divergence between distribution over trajectories we had before the change under theta and then after the change under theta plus delta theta. Why? Well, how is our gradient computed? It's based on rollouts from policy pi theta. And so the gradient approximation is based on data under theta, which will only be valid if, well, the new policy collects similar trajectories. If the new policy collects very different trajectories, then that first-order approximation will not be very valid. And so what does it mean to collect similar trajectories? It means that the KL divergence between distribution over trajectories under new and old policy is small. So you think about some intuition here. You can imagine some action that you're taking that doesn't really, in some state, the action you take doesn't affect very much what the next state is. Well, that action, you got a lot of liberty in terms of changing that because you're not changing your trajectory distribution. But if in some state the action you take has a massive effect on the states that come after, then changing the action distribution in that state will have a very big effect on this KL divergence. Okay, so how do we evaluate this KL? Well, let's see what it is. It's distance between well, it's kind of a pseudo distance between distributions over trajectories. The probability of a trajectory is given over there. It's a product of the probabilities of action given state and next state given current state and action. The KL is a expected log probability ratio of the two distributions. Well, let's fill in our expression for the probability of trajectory. Fill that in. And now, again, something magical happens. The magical thing that happens is that the dynamics, probability of next state given current state and action, cancels out in that ratio. So we, again, don't need to know the dynamics model to evaluate this distance, this KL divergence. which is really nice. We have the same thing happen in the policy gradient calculation itself, where the dynamics would disappear as we do our calculation. Then you might say, well, isn't the dynamics still sitting up front, the probability of a trajectory under policy pi theta? Yes, it is, but that's an expectation, right? And so we can just do rollouts under our current policy and evaluate an approximation to this expectation from samples, and this is what we have. So the expected log odds ratio of probability of action given state under old policy over probability action given state under new policy. Okay, so what does it give us? We have now turned the top objective into something much more concrete, where we know we have access to all the quantities. We get these quantities from our rollouts. The gradient we've seen on the board just before, how to get it, and then that log probability ratio, well, we just look at our rollouts and we look at the ratio. We can just insert it right there. So now, how to enforce this constraint given we have some complex policies like neural networks? Well, we've seen constraint optimization, and so we can in principle run some constraint optimization, but it's pretty complex to run it for this. So in the TRPO paper, it was shown that one way to do this, and that works quite well, is to have a second order approximation of the KL divergence. So that KL divergence shown there, the log probability ratio, second order approximation. At that point, you have essentially a squared condition. You essentially have something of the form that a squared deviation should be small, but a measured by the Hessian squared deviation from the previous setting of theta. So first order approximation is kept constant, meaning that it doesn't change. There's nothing second order happening there. It's just first order. And then the Hessian here is actually called the Fisher information matrix, because Hessian of the KL divergence, that's just what it happens to be. And it looks like this. So it's fairly straightforward to compute, in the sense that to get the Fisher information matrix or the Hessian here, all you need is gradients. You never need to compute actual second derivatives. Now, these gradients will be multiplied with your transpose and build a big matrix. And if you have a large network, that's still tricky to deal with, because a matrix, if you have 1,000,000 parameters and you have a matrix of 1,000,000 by 1,000,000, it's pretty big, a lot of things to deal with. But we'll see how to deal with that soon. So what we then have is the second order approximation for the KL, and which can be obtained from gradient calculations. So our problem now is the following. We maximize this locally linear objective subject to this second order constraint. Okay, are we done? Well, when theta is high dimensional, inverting this f theta is somewhat impractical, which you would have to do in kind of the canonical way of solving this. Because the canonical way of solving this would say that actually your step direction should be f theta inverse times g hat. And then you just need to find the right step size, which epsilon determines. So we need an efficient scheme to find effectively the f theta inverse times g hat. Conjugate gradient can do this for us. Can we do even better? We can do even better than that. So now at this point, we know how to solve the problem above using conjugate gradient, which is a standard optimization method. But can we do even better? Well, we can. We saw that we could use a more precise surrogate loss, not just the gradient approximation, but an actual surrogate loss that's closer, such as the log probability of action given state in the surrogate loss, or the importance ratio. So let's take a look at that, and that'll give us the full TRPO algorithm. Here we are. So we have maximize over pi, or called pi theta, it's just called pi here, the surrogate loss, which is the expected value under pi theta old. What does this mean? We're going to have samples that approximate this expectation. For each rollout, each action and state we have, we're going to have an entry in this objective, which is the probability under the new policy of action given state. That's what the neural net prescribes, divided by a fixed number. Here, pi old, action given state, and then multiplied by the advantage under the old policy. Okay, so then we have a constraint, the KL divergence should be small, so we don't want to move too far away from our previous policy. Full algorithm, run the policy for t time steps or n trajectories, estimate the advantage function, which we know how to do. It's essentially the sum of rewards from that state onwards minus the value function. Then compute the policy gradient, which we know how to do, or you can put in that surrogate loss objective, depending on what you do. Then you can run conjugate gradient to optimize the surrogate loss, or just use the first order approximation. Then we do a line search on the surrogate loss and the KL constraint. So it's a little bit complex, but it's actually a very well-motivated method in the sense that you now clearly define in which region you trust your local approximation. Within that region, you're going to find the optimal point, move to that, and then get new trajectories, which gives you a new region in which you can trust your new surrogate loss and repeat. One of the big things this did for reinforcement learning was effectively that reinforcement learning can be a bit unstable if it's not run carefully, if you have bad step sizes and so forth. And this allowed to have a very kind of stable algorithm that can reliably optimize our objectives. And so these are some of the first results obtained in optimizing policies for these Mujoko environments, which has since kind of morphed into OpenAI Gym. But at the time, OpenAI Gym didn't even exist yet. It was all straight up Mujoko. And you see here policies learned by TRPO that are, I think, about neural nets with about 100,000 parameters in it that have been trained to control these robots. Here is the learning in action. It's more dancing than walking, but it's optimizing the objective gradually. And actually then learns to run pretty well. Now, actually I think this is the same video we just watched. Here are the learning curves. The green and blue are two versions of TRPO. Vine and single path is what they're called here, because there's different slide variations of how to run it. We see that they are learning the fastest. Sometimes there's a bit of a tie still with some past reinforcement learning methods at the time, but they're always among the fastest. This is for the simpler environments, car, pole, and swimmer. Then going to more complex environments, hopper and walker, we see that they strictly dominate compared to past methods. The beauty actually was that with this method, you can not just train for Mujoko environments or simulated robots, you can actually learn to play Atari games just as well. So it's a very general approach, whereas at the time, the Q-learning methods, for example, DQN that had learned to play Atari games, not very clear how to make it work for the simulated robot environments, because they have continuous action outputs, and DQN has a network that has a Q value output for every possible action. But if you have continuous actions, you cannot have a Q value output for every possible action, because you need infinitely many outputs, which doesn't work. Then, in addition to TRPO, which we just saw, to solve a more complex problem like humanoid, what was needed was to add the generalized advantage estimation that we covered last time. So when we look at the policy gradient estimate, there is a sum of future rewards, which is the Monte Carlo estimate minus value function. Replace that sum over future rewards, keep the minus value function, but the sum over future rewards is replaced by an exponential weighted average between sum over all future rewards and the bootstrap versions of immediate reward plus value, immediate reward plus next reward plus value, immediate reward plus next reward plus value, and so forth. And exponentially averaging those give a much more stable and sample efficient estimate of the advantage function, and allowed us to get the first results on a much higher dimensional problem like humanoid. And here you see it actually gradually over time learn to control itself and learn to run. It's very interesting because at the time, this is 2015-16, all the work on legged locomotion was based on much more traditional methods. People weren't really using reinforcement learning to have a robot learn to run. They were just thinking about static stability, dynamic stability, center of mass, support triangles, things like that to try to come up with good designs of control policies. But this showed that if you can train long enough, and it of course requires a bit of data collection and training, you can actually learn this rather than having to design this by hand. There's a little bit of extra intuition there to some extent, is that if you look at traditional control methods, what's very popular? What's very popular is either you hand design something very crafty, but that's often hard to do. What else is popular is linear controllers. But the linear controllers are limited in what they can do. So there might be time-varying linear controllers. But is time varying really what you want? It really depends on the state that you're in, which linear controller you should use, not on the time. And in some sense, that's what a neural network does. A neural network essentially has a bunch of layers that process the state you're currently in, and then at the very last layer, it outputs a linear controller. And so effectively what you're doing with a neural network is you're selecting the right linear controller for the current situation. At least if you have values, that's effectively what's happening. And so it's in some sense not too surprising a neural network can do well at this with values, because people were already all the time in the past designing compositions of linear controllers. It's just that now we let the neural network decide on the composition rather than try to do it by hand. And so people would do it in the past with linear time-varying controllers, or with hybrid systems where you decide on a mode that you're in, and within that mode you have a linear feedback controller. And this is actually much more flexible, because if you think about it carefully, the neural network processes the state, and it doesn't directly switch from one linear controller to another one where you switch modes. It's a very gradual thing. It's along one axis in a high-dimensional space that you just make one change. And so it's a per dimension, but not axis-aligned dimension, changes to the linear controller, rather than one linear controller to the other one to the other one. Very gradual changes in comparison to typical hybrid control systems. Now, of course, it took a while to figure out how to optimize the parameters in a neural network in a reliable way that you can find this automatically. But in some way, in hindsight, it shouldn't be too surprising that this is possible, because people were already trying to do very similar things by hand. Now, what do we have left? PPO. PPO is, I would say, one of the main current methods that people like to use. It's probably the most advisable method to use if your data collection is fast. So I would say right now in reinforcement learning, there's not a single method you'd always favor. It really depends on the situation you're in. If your data collection is really fast, almost instantaneous, then PPO has a lot of advantages. We'll later see that off-policy methods can be beneficial when your data collection maybe is a little more expensive, a little slower, because you'll reuse your collected data more often. But intuitively, if your data collection is very fast, what's the point in reusing old data? You should just get fresh data under the current policy and keep optimizing from there, rather than try to get a little more signal out of your old data. And so when your data collection is fast, as we will see in some results later, OpenAI's DOTA 2, or the OpenAI in-hand manipulation efforts, which is learned in simulation, very fast data collection, then PPO is the natural go-to method. So let's write out what exactly it does. Actually, let's first maybe argue why we're not totally happy with TRPO yet. It's not that easy to enforce a trust region constraint for complex policy architectures, especially ones that have stochasticity like dropout, or have parameter sharing between a policy and a value function. So that's an inconvenience. You often want parameter sharing. Conjugate gradient implementation is complex. Yes, I mean, John Schulman definitely got it working beautifully, and you could maybe reuse his code, but it's nice if we could have methods that are a little simpler to implement, and at the same time maybe have other benefits. For example, we look at standard neural net optimizers like ADAM and RMS prop. They're really, really simple. What if we could just rely upon them instead of on a conjugate gradient method to solve our problem? Let's see what we can do. So I'm going to write out the TRP objective again, and then from there we're going to go to the version 1 of the PPO objective, and from there we'll go to version 2 of the PPO objective. So need a lot of space here. Let's see. TRPO. What does it do? Well, we max over theta our empirical expected value in our algorithm, and ideally we'd have the exact expected value, of course, but in practice we have rollouts. Empirical expected value of pi theta at given st over pi theta old at given st. This is overall times and counted in any trajectories times our estimate of the advantage of taking that action AT in state ST. And again, advantage would be roughly rewards you got then onwards minus the value of that state. But it could be more sophisticated, like in generalized advantage estimation, we have a combination of sum of rewards and reward plus value and so forth minus the value function. And then subject to that the expected value, empirically again, because that's all we have, of the KL between the old policy, pi theta old, and pi theta new, evaluated in the states that we visited, is smaller than some delta. Okay, again, the reason this is kind of annoying to optimize is because constraint is hard to enforce, a lot of extra machinery needed to make that work, and also if you, let's say, think, okay, maybe I can do this with a second order approximation, still with a high dimensional policy, that second order approximation is still something very big and difficult to deal with. So what can we do? We've actually seen something similar before. How can we turn a constraint optimization problem into an unconstrained optimization problem? We can form the Lagrangian. So instead, we can say maximize, let's see, well, let's write it here. Maximize over theta, expected value, and then same thing as we have on the left. But then we have Lagrange multiplier beta, and then again, same thing we have on the left. So we know that if we pick the right choice of our Lagrange multiplier, the exact right choice, of course we might not know ahead of time what it's going to be, we've picked the exact right choice, the optimum of this objective is the same as the solution to the constraint optimization problem. So if we can just find the right beta, we're good to go. How do we find the right beta? Well, we have seen something called dual descent. And what does dual descent do? Well, it puts a min over beta up front here. And in this case, because it's an inequality constraint, beta is going to have to stay positive. We put a min over beta in front there. And then we say, well, we're going to alternate. We're going to do some updates on theta. And then after that, we'll do an update on beta. And the update on beta will be informed by, effectively, the gradient of this thing, which will look at whether on average this is satisfied or not, whether the expected KL is smaller than or equal to delta. That will determine the sign of this thing. And so our beta will go up or down depending on whether we are satisfying the constraint. Often it's done a bit more heuristically and not through an actual dual descent. And people will just say, okay, I run some updates on theta. After I do some updates on theta, I check, are my constraints, is my constraint satisfied? If so, clipping, then my beta can be a little smaller, doesn't need to push as hard on making sure the constraint is satisfied. And if my constraint is not satisfied, let's just crank up my beta a little bit, and hopefully in the next round, when I do some more updates on theta, I'll get something that satisfies the constraints. So it'll just be some kind of periodic nudging of beta. What's the beauty? Once you have an objective like this, you can just feed it into any first-order optimizer or close to first-order like Atom or RMS prop. You just give it this objective as a function of theta, let it do a bunch of steps, then you nudge your beta, and then you collect your next set of trajectories, and now again, with your new beta, you let the optimizer do a few steps over theta, you nudge your beta as needed, and keep repeating. Now, one reason this might still not be fully satisfactory is because, I mean, this is still a bit of stuff to deal with. Can we make this even simpler? So how can we make this even simpler? Let's see. If I think carefully about what's really happening, is that we're trying to ensure that we keep our policy pi theta close to our old policy pi theta, while, of course, moving a little bit away to improve our score in the objective. So in some sense, what's happening here is that we don't trust our objective when we're too far away from the old pi theta. If we're too far away, we don't trust it. And that's what the second term is trying to do. Can we write this in another way? So this is the most popular version of PPO that's most often run these days, is to say, OK, let's start again from those first principles. And let's define this thing called our R, our ratio, RT theta, as pi theta AT given ST over pi theta old AT given ST. So R at theta old is equal to 1. 1 is the center point here. All right, not 0, nothing else. 1 is the center point. If you stay where you were, this ratio is 1. It's the importance ratio. So really what we want is, in some sense, if we look at that objective, maximizing this R times the advantage, we want R to stay close to 1. If the ratio stays close to 1, we can trust our objective. If it's away from 1, we don't trust it. We can actually do this on an individual per term basis. Any term in the objective where the ratio is away from 1 too far, we cannot trust anymore. Any term where it is still close to 1, we can trust, and we can nudge based on that term in the objective in which direction the policy should go. So here's the PPO objective called L clip, because there's some clipping happening. This is again a surrogate loss. We have a bunch of trajectories just like their surrogate loss. It's going to be, again, an expected value. But now what we're going to look at is clipped version of RT theta between 1 minus epsilon and 1 plus epsilon times A hat T. It's going to be a little more to it, but let's parse this part first. What is this saying? Let's say no clipping is happening. There's no clipping happening. We're close enough to 1 that no clipping happens. Well, then it's really just this objective again, this term here. What is happening? If I nudge theta to get somewhere where for a specific time, so specific action and state pair, this ratio moves too far away from 1. It becomes, let's say, bigger than 1 plus epsilon. What's happening? It means that we've been pushing up the probability of that action. Like if this grows higher and higher, it means that that was probably an action with a great advantage. We keep pushing up the probability of that action, but we don't want to keep pushing it because we can't trust this too far out. And so once we pushed it so far that pi theta action given state has become 1 plus epsilon, this thing will clip, meaning that the dependence on theta will disappear. And when we look at a gradient of the objective with respect to theta, that term will not contribute anymore. So even though if we didn't clip, this term, due to a large advantage here, let's say, would try to keep pushing us to higher and higher probability on AT given ST, due to the clipping, the optimization won't have access to that signal anymore, and it won't continue to push in that direction. So the maximum you can do effectively for any action given state, kind of the maximum you can do is get to a ratio of 1 plus epsilon. That's not entirely true. If there is a lot of other evidence in your objective, you could still be pushed beyond 1 plus epsilon, but on your own, this term in itself will not be able to contribute beyond reaching 1 plus epsilon. After that, the term stops contributing to the objective. Again, it's a little subtle because it's not like you cannot go past 1 plus epsilon. You could, but only if other terms in the objective push you there. Because yourself, once you're 1 plus epsilon, you disappear from you have no derivative anymore because you become a constant. Theta disappears in your term. And when theta disappears in your term, the gradient respect to theta is 0, and you don't get to contribute anymore. So that's the key idea. Same in the other direction. If an advantage is very negative, then naturally you'd be pushed towards lower values, so the probability would be driven down, below 1, lower, lower, lower. Once you hit 1 minus epsilon, this term, due to clipping, will stop contributing to the optimization. And so it's still possible you keep going down if there's other terms in the objective that drive you down, but you cannot on your own, by just having one very negative advantage, try to drive it down on your own very far. Now, what else is there in the objective? There's a little bit extra, which is that there is here an extra min over this objective, which I just described, and the original objective, RT theta A hat T. Okay? So what does that mean? We're really maximizing this, right? We're trying to maximize this over theta. So by having this min here, it's saying that, well, as I introduce this clipped objective, just in case it introduced some weirdness where I become overly optimistic due to clipping the effect of some actions in some places and somehow it works out in my favor in a way that I didn't anticipate, well, this is making sure you're never being more optimistic in your overall objective than what the original thing would have said, because you take the most conservative of the two estimates of your objective. In many ways, this is very complex because there's a lot of symbols there and there's a lot to parse. But from an implementation perspective, this is really, really simple. Because now all you do is you collect a bunch of rollouts. For each rollout, at every state action pair, you compute the advantage, which we know how to do. And you retain, for each state action pair, you retain a state action pair as well as the advantage. And then you just build up your objective. This thing here, you feed it into an optimizer like PyTorch TensorFlow, and it'll just do the work for you. And you take a bunch of steps on this objective, and then at some point, you get new rollouts, fresh data, and repeat. Any questions about this? Yes?
So this kind of quicken or trust bleeding, is it? If the performance is depend on the first trajectory?
Not sure I understand the question. Maybe I'll give you the mic because it sounds like we might need some iteration here.
So my question is this kind of the algorithm depends on the first trajectory? So it depends on all your trajectories. So every rollout you do will show up in the objective. Now, if your question is, does it depend on the initialization of your policy, and does it find a local optimum versus a global optimum? Absolutely. These are local optimization methods. And so if you have a very bad initialization, it might find a not so great local optimum. And of course, a lot of tricks people play. They might initialize some demonstrations, so supervised learning to match demonstrations, and from there optimize the policy, or they might do reward shaping, which introduces more signal into the trajectories, or they might have a curriculum where they first solve easier tasks, then harder tasks. A lot of tricks like that to alleviate that. But yeah, ultimately, this is a local optimization method, and so you'll have to be aware of that when you run it, and not count on it on its own being a reliable global optimization.
So because of the min, it seems like the clipping on 1 plus epsilon is doing something, but then the bottom, the lower bound clip of 1 minus epsilon. So like if r t of theta is less than 1 minus epsilon, the min would make the lower bound clip not do anything. Is that true?
Let's see. Let me think about that offline. It's possible. It's possible that we need to change the parentheses slightly on this. Let me think about it offline. All right, then let's take a break. And in the second half of lecture, let's look at off-policy methods. All right, let's restart. Let's first look at this again here, and the question about could this 1 minus epsilon, and how does that interact with the ratio here? So we need to think through all the possible scenarios with this being positive, negative, and then the ratio being driven up or down. And so I think the regime that you're curious about where this kicks in is when this is actually positive. So it's a little counterintuitive, but this is positive. It's very positive. You, principle want to drive the probability up, right? But you have many, many samples that contribute to the objective as you take your gradient steps. It turns out even though this is positive, you're driving down the ratio. Just counterintuitive, and just think about this term, it could never happen because there's a lot of terms in the objective. It's possible that this is positive, yet nevertheless you're driving down this probability due to some trade-off with other terms in the objective. Then you might decide, because you get clipped at 1 minus epsilon, that you're happy to indefinitely drive this down. Even though the advantage is very, very high, you might be willing to drive this down, the ratio down. If you just have this part, might be willing to drive down that ratio really, really low, because worst case, you just end up at 1 minus epsilon. It doesn't go very bad. That's where this one will kick in, because then this term here, as you keep driving it lower and lower below 1, this one will be lower than this one. And so it's a very counterintuitive setting because it's essentially advantage positive, yet the ratio is being driven down because of other terms in the objective that are somehow dominating, and you don't want this to be completely ignored. And by the clipping, you would get completely ignored when you really shouldn't be ignored, and then this thing kicks in over here. So that's where it kicks in on the 1 minus epsilon side. Another question, yes?
What do you mean by other terms?
So the objective is an expected value, and so each term in the objective is of this format, but really all the data we collected consists of state action pairs followed with an advantage. So after we do our rollouts, so after the rollouts are done, what happens is you do rollouts, and the results of the result of the rollout would be things of the type ST, AT, and estimated advantage for that slot. And those are the things you keep around. You might also keep your policy evaluation around because you know you're going to have to backpropagate through it, but maybe you don't. You just store it, and then later you redo the forward propagation and backpropagation. But this is key. This is what you have to store from your rollouts. Every one of those contributes to this objective. This expectation here is really a weighted sum, an average of each of those experiences contributing. And so each one individually has this complex structure. So this complex structure is not happening on the outside of it, it's happening in each individual term. Looking at each individual term, can I still essentially trust that ratio for this individual term, or am I hitting the bounds of 1 minus epsilon, 1 plus epsilon? And then the extra thing that's happening that's quite important is that you don't want to let other terms take advantage of the fact that this term's getting clipped and just completely dominate some optimization, making this one in principle really bad, but by the clipping it would not look bad. And so that's where this one will kick in. So let's take a look at another class of methods, which is off-policy methods. Within off-policy, there'll be two types: Q-learning and kind of Q-based policy gradients, or Q-based actor-critic, whatever you want to call it. So this is the outline, and we'll probably get through the first 3 bullet points today, and then we'll do the next 3 on Thursday, and wrap up RL on Thursday with also some model-based RL. So what's the storyline? TRPO, PPO, there's an important sampling surrogate loss, which allows us to do more than a gradient step, but it's still very, very local. If our data collection is super cheap, that's fine. We do a local step, collect new data, and repeat, and that's the regime where you're going to want to use PPO. We're going to have the best wall clock time. Again, it's something, if you look at papers, people usually put sample complexity, but very often in practice you care about wall clock time. And so often in today's papers, sample complexity on the horizontal axis, you'll see something like Q-learning or soft actor critic dominate PPO in terms of sample complexity, but wall clock time is a whole different thing, and so often PPO will easily dominate on wall clock time if sampling is cheap. So what if we do care about sample complexity, though? It is expensive to get samples, or it's slow to get samples. Could we reuse our samples more, do something more globally off policy? The important sampling is somewhat off policy because we get data from one policy and we optimize another policy. It is off policy, but it's very limited off policy. So what can we do? Yes, we can actually do something. Remember the dynamic programming structure when we run value iteration or policy evaluation? It looks at the per time step breakdown of the process. Once you do a per time step breakdown, you can actually start reusing things a lot more. Because a per time step breakdown, you're simply looking at the dynamics of the system from time t to t+1, and that's reusable much more easily than a full trajectory, because a full trajectory, well, that was trajectory was collected under a current policy. And so that sequence of transitions would be very specific to the current policy. But individual transitions could in principle happen under any policy as long as it's not a deterministic policy. Any stochastic policy could in principle have any transition happen. So these individual transitions you should be able to reuse, repuzzle together to evaluate a new policy in a more fundamentally off-policy way than we've done so far. So Q-learning, and DQN is a deep neural network version that was the first successful one. That looks at the one-step sampled off-policy Bellman backups, can do more sample reuse as a consequence, more data-efficient learning directly about the optimal policy. And we'll look at that in a moment. I want to give you a whole story before we start, and then we can look at the details. So it looks at per time step Bellman updates, trying to learn about the optimal policy, looking at the Bellman update equation. So why wouldn't you always use this? If you can use any state action, reward, state transition to learn about the optimal policy, why wouldn't you always just do that? Well, it's often a bit less stable. Because you can imagine that if your optimal policy is very different from the policy you collect data under, that you don't necessarily get a whole lot of signal in these one-step updates. Because if you're always taking action 1, the optimal policy is supposed to take action 2, well, this data that's always taking action 1 is not telling you a whole lot about what would happen when you take action 2. And your optimal policy needs to learn about that. So there's still limits in what you can learn. If your data doesn't support it's extracting the signal, it's just not going to be there. So there's some limitations there, and it's often a bit less stable. So as a consequence, often something intermediate is very popular, which is you still look at the one-step transitions like Q-learning, but you do it off policy around the current policy. So essentially look at, and we'll look at the details soon, or next lecture, but it's essentially looking at the Bellman update equation for a policy improvement. Remember we had policy evaluation and improvement in policy iteration. That's what the second thing will be about, whereas the first thing, Q-learning, is about the update equation with the max in it, the evaluation update equation. The second thing will often be a bit more stable because your data more directly supports giving you the signal you need to do local improvements. Yet they can be a bit more off policy than PPO or TRPO because it's not evaluating based on these entire trajectories, which are very much on policy then, but based on single step transitions. And so there's a few different ideas at play here. We'll recap this again later once we've seen it all in detail. So first thing we need to figure out is Q learning. What's Q learning? Well, quick recap. What are Q values? The Bellman equation tells us that the optimal Q value, Q star SA, is the expected sum of rewards you get from starting in state S, taking action A, and acting optimally then onwards. And we know that it satisfies this equation over here. So we can find the solution to that equation. We know what to do, because then we just take the action that maximizes the entry of Q star SA for current state S. How can we find it? We actually saw this in one of the very first lectures. You can run Q value iteration rather than V value iteration, shown here, and that will converge to the optimal Q values. Now, of course, a little bit of trickiness here that if the state space is large, you cannot loop over all states and actions to do this update, and definitely not multiple times till convergence. And so what are you going to do? Well, there's a bunch of things you might want to do. But in terms of intuition, let's look at this over here. We have an expectation here, a sum over possible next states. You can imagine that maybe we can replace this expectation by a sample estimate of that expectation. And you can imagine that maybe rather than looping over all possible states, we'll actually have a neural network approximating the Q function. And so hopefully it'll generalize to states you didn't do an update for. All right, so first we'll do the tabular thing, no function approximation yet. What's happening here? First equation is again the standard value iteration with Q values. We rewrite it as an expectation, so exact same thing, nothing changed, we just write it as an expectation. Once it's an expectation, we're going to say, oh, really what we're doing is we should average that thing on the right-hand side to get an update for the thing on the left. Well, okay. We have a state action pair, and we get the next state S prime. We consider our old estimate that we have so far for the Q value for SA. And we can say, well, we need some average of reward plus max over actions Q value at the next state. Well, we're going to take a sample average from one sample. We say, OK, we call it our target. The reward we experience plus gamma times the max over actions of the Q value in the next state. That's just one entry of the average that we want to compute here. Just take one entry. Use that as our target. Now using just one such outcome, one sample, is not going to be very precise. So we don't want to update all the way to that sample value because we need to average many. The way we're going to average is by saying we had an old estimate. We retain mostly the old estimate. So alpha might be something, I don't know, 0.1 or something. So we mostly retain the old estimate and then slightly nudge it towards what this current sample said it should be. And then we just collect data. That's all I need to do. You just collect a ton of data and just keep running those updates. And it turns out for tabular Q learning, if you run this long enough and under certain technical conditions, this is guaranteed to end up at the optimal Q values, Q star, for each state action pair. So very, very simple. Now, full algorithm, you start with some Q0 SA for all state and actions. This is our initial Q values. It's just a big table with an entry for every state and every action that can be taken. Then you get an initial state in your MDP. And then you repeat. You sample your action, get the next state as prime. If it's a terminal state, well, then there's not going to be any Q values happening afterwards anymore. So then your target value is just a reward you got in that transition. That's it. If it's not a terminal state, and then you have to restart. If it's not a terminal state, well, then the target is going to be reward plus max over Q values at the next state, maybe discounted. We collected our target value from this one experience. Then we nudge the Q value at SA in the direction that this target prescribes. And we repeat. That's it. That's Q-learning. Very simple to implement. It's very nice because it's very few lines of code, and it's guaranteed to converge unless some technical condition to the right thing. Okay, how do we sample our actions? Well, maybe choose random actions. That could work, maybe. You could also choose an action that maximizes the current Q value at the current state. It's called the greedy approach. Why is it called greedy? Because you're trying to take the action that maximizes the reward you're getting now, based on what you learned so far. But greedy isn't always the best, because maybe what you learned so far is not that precise yet. And you really should not be optimizing for reward right now. You should be taking actions that allow you to get information about other rewards you haven't learned about yet. That would be called exploration. So epsilon greedy is something where you choose a random action with probability epsilon, and otherwise you choose the action greedily. So what are some properties? And epsilon greedy is very popular. So the simplest implementation of Q-learning would be you run epsilon greedy for action selection, maybe epsilon initially pretty close to 1, because initially you have no idea what to do. You shouldn't trust your Q values. And then over time you anneal it down to become closer and closer to 0, because your Q values have more and more converged. All right, what are some properties? Some very good properties. It converges to the optimal policy, even if you're acting suboptimally at all times. Even if you never care about acting optimally, you'll still find the optimal policy. Why? Because we saw the update equations, and we know this is a stochastic approximation that over time converges the solution to the original equations, which find the solution to the Bellman equation, which is the optimal Q values. This is called off-policy learning, because you have to never even act optimally, yet your Q values at some point will somehow encode the optimal Q values, hence the optimal policy. Some caveats. Well, you have to explore enough. It's not like it works off-policy in the sense that let's say, you need to find an optimal policy for cooking in the kitchen, and you're always going to the bathroom taking showers, and that you can take showers to learn about cooking. That's too much off policy. You need to explore all state action pairs a lot. So you have to eventually make the learning rate small enough, otherwise it keeps hopping around and doesn't really converge. But assuming you explore enough means you visit every state action pair infinitely often, which is a lot. But that's the technical condition. In practice, just visiting them frequently is good enough. And you make the learning rate go to 0 over time. But not too quickly, because then you don't learn about enough things. You only learn about your early experience. So gradually decay the learning rate. To make it a little more technical, we need to visit all states and actions infinitely often. But it doesn't matter how you select actions. That's just, you need to make sure there's enough exploration. You visit all states and actions infinitely often. And the learning rate schedule that you could use is this thing here. You ensure that your alpha t, where t indexes over time in your experience, alpha t's sum to infinity, meaning that, what does that mean if this sums to infinity? It means that imagine you're at a current time, I don't know, some time capital T. And maybe you've had nothing but bad luck so far. Your exploration's been unlucky, the data you've collected is unlucky, you've had all the unlikely events happen to you that are not representative of how the world works. Sometimes, flip a coin 10 times, it's 10 times the same side, right? So let's say all this stuff happened in kind of a not really the way you'd expect to want to learn from. Well, from that time capital T onwards, you still have learning steps available that sum to infinity. At any given time, the learning steps you have in the future ahead of you will together sum to infinity. That's what it means, this first condition. So no matter how unlucky you were in your experiences, you still have enough learning capability left in the future to compensate for it. Then the second thing ensures that the variance of your estimator isn't infinite. Because if you have infinite variance on your estimator, well, then you're not going to get convergence to some nice final result. So how can you achieve this? If alpha t equals 1 over t, you have something sum over t, 1 over t sums to infinity, but then sum over t, 1 over t squared is finite, and so that's one way to achieve it. You can refine this. You can say, oh, maybe 1 over the number of times I've visited a state action pair so far. Because really, your learning rate should depend on that specific state action pair, how often you've been there, not in general necessarily how long you've been learning. OK, so and there's some nice papers proving those theoretical guarantees. So let's look at this in action. Here's a simple robot. This robot has 2 actuated joints. It's essentially an arm, and it can try to crawl. So it's a very simple locomotion task. It's a very low dimensional problem, only 2 variables that we get to control, 2 joint angles that we can increase or decrease. So we can actually discretize this and then run Q-learning in the discretized space. The simulator under the hood will still be the continuous simulator, but when we run our Q-learning, we look at discretized states, 2-dimensional discretized states, and 2-dimensional discretized actions. Oops, video. So here's it in action. We see epsilon at the bottom left, one of those hyperparameters we have in Q-learning. Epsilon equals 0.8, meaning we mostly take random actions. So it's mostly doing random actions here, not very dedicated to what the Q values are saying would be the right thing to do. So it's really focused on exploring. We see gamma equals 0.9, so roughly cares about rewards up to 10 time steps into the future. And then our alpha is 1 here. Then at some point in this video, very soon, we'll see epsilon start decreasing. What do you expect to happen when we decrease epsilon? Well, we take more exploitation actions, less exploratory actions. And so what we expect to happen that if it collected enough data, if it visited every state action pair infinitely often yet, then it should have the optimal Q values already in there, and when it starts listening to them, it should do pretty well. And we see indeed, I mean, it didn't visit everything infinitely often, but it visited everything sufficiently often that when we decrease epsilon, we see actually what is in the Q function, and it actually does quite well. And with epsilon equal to 0, just directly listening to the Q function, it learns to crawl very effectively, or it executes crawling very effectively. Under the hood, we can also look at the Q values changing over time. So on the left is the values. So horizontal axis, vertical axis correspond to discretization of the 2 angles in that robot arm, the 2 joint angles. On the right subplot is the Q values, which relate to whether you increase or decrease specific joint angle. We accelerated here, and we see that at some point we have some region with very good value and Q value, and other regions with very bad Q values and values, because that's where it's not in a good situation to move forward fast. All right, so that's an example of this in action. Now, if you want to do this with more complicated problems, you're not going to be able to tabulate everything. So imagine grid world, sure, OK, 10 states, no problem. But Tetris, 10 to the 60 states, well, you cannot tabulate that. Then Atari, 10 to the 308 states in RAM state measurement, or if you do it in pixel space, 10 to the 16,000 something states. Nobody can tabulate that. It's just impractical. All right. How about continuous? Well, again, crawler, it's OK. About 100 states, not too bad. Hopper, 10 to the 10 states, if you discretize in a reasonable way. Yeah, that's becoming pretty hard to do, rather impractical, I would say. And then humanoid, completely impractical. So we need something else. So we need to generalize across states, and we've seen this before. So instead of having a table with a Q value for every state action pair, we need some kind of function. So we don't want a table for everything in memory. We want some kind of function that generalizes. How are we going to do this? Well, we're going to have to do approximate Q learning then. If we don't have the Q values available, we need something that approximates them. So we have a parameterized Q function, Q theta SA. OK, so what do we do with this? Let's say it's a linear function. Then we just have a weighted sum of features. But it could also be a neural net or a decision tree and so forth. Doesn't really matter. Same methods will apply. What's our learning rule going to look like? Remember, Q-learning was very simple. We collect data, and for every state, action, reward, state combination that we experienced, we computed a target value, and then tried to update towards that target value. We're not going to get to update a tabular entry towards the target value, but for every state action we had, there's still a function value, Q theta of SA, and maybe we can nudge that Q theta SA in the direction of the target by updating theta. That's exactly what we're going to do. We'll compute our target value, and then we nudge in that direction by saying we have an objective, could be a squared loss, could be a Huber loss, and we say we need to nudge the Q value for that state action pair in the direction of the target. We do a gradient update, and then next data, another gradient update, or maybe we do it with mini batches and so forth. All right, let me pause here. This is the foundation for everything Q learning. Let me make sure this slide is clear, especially the bottom equation there. All right, so we have our basic algorithm now. We can just do rollouts, and while we run our rollouts, we can just do these updates, and that should be our approximate Q learning approach. Now, this is what we had, but kind of spelled out more bigly, so bigger font version of what we just had. Now, let's say we want to run this. Here's what it actually looks like as an algorithm. And let's step through that so we know exactly what it does. So we initialize our replay memory. This is DQN, so don't worry too much about it. It's some memory we keep experiences in. We initialize our action value function, which is a neural network that takes in state and outputs a Q value for every possible action, so a discrete action space. Then we initialize a target action value function. So we'll have two neural nets, it turns out, in some sense. Okay, so we keep track of two neural nets that look the same but have different parameters. Then we initialize our sequence, some start state. Don't worry about the phi's. The phi's is just, this is for Atari. So in Atari, if you just look at the current frame, you don't have information about velocity. You don't know where things are moving. You need to look at a sequence of frames to see where things are moving. So essentially, what it's doing is it's turning, instead of looking at one frame, it's saying we need to look at 4 frames and look at the 4 frames together. That's really what the phi thing is doing here. OK, so we iterate. Probability epsilon, select the random action. Epsilon greedy. Otherwise, we select the action that maximizes the Q value for the current state that we're in. Then we execute the action. We observe a reward and image that we experience at the next time. Then we do some processing here to combine images to have 4 images in sequence rather than just 1 image, so we can see the velocity of things moving in the screen. Then we store that transition, which is effectively state, action, reward, state at the next time in our replay buffer. So this is our experience collection. Then we do some learning. We go to our replay buffer. We take a bunch of those transitions, and we're going to learn from them. For each transition, we look at computing the target value, which in DQN paper they call Y. So for each experience, we compute a target value. If the episode terminated at that time, just look at the instantaneous reward. If it did not terminate, look at reward plus Q value at the next time. We now found our target values. Now we set up our regression objective. We want our Q function to get closer to our target values. We do a few gradient descent updates or Atom, RMS prop, and so forth updates on the network parameters. And we've done our learning for this iteration, and then we repeat. Now there's one extra thing happening here, that there is this 2 Q functions. There is Q and Q hat. What's the deal there? Well, because your target is computed from your Q values, you have this loop happening. You take targets from your Q values, you update in that direction, and this process repeats, and this can often be unstable. The way to make this more stable is to say I'm going to have a old Q value from a little while ago, keep that fixed for a while, and use that to compute my targets. Or you might compute a Polyak average, use a running average over your past Q values, and use that Polyak average as your target. This will stabilize the learning so you don't have this feedback loop that's going too quickly. There's still a feedback loop over time, because at some point, you use the new Q value function into the old, but that happens with sufficient delay that this feedback loop is more stable than it would be if you do it instantaneously. So that's Q learning. This was done with Huber laws instead of quadratic laws, and annealing the exploration rate down to 0 or close to 0 using RMS prop instead of SGD. Putting this all in place resulted in the first very big result in deep reinforcement learning, the Atari results from DeepMind, showing it's possible to run this DQN algorithm for a neural network from its own trial and error to learn to play a range of Atari games. Architecture underneath, very simple, just convoluted, much like AlexNet, the slightly smaller one. But through the learning updates and getting that exactly right, stabilizing Q learning with the 2 Q functions and doing everything just really right, made it work. Achieved superhuman performance on a wide range of Atari games. Just run the same algorithm, no change on many of the games. It'll actually achieve superhuman performance, which is pretty amazing. Let's see. Let's stop here for today, and then we'll look at variations on DQN on Thursday. Oh, one quick other announcement. On Thursday, we'll have, after lecture, a interesting demo. So on Thursday, a friend of mine from Miami/New York is coming by, and many of you probably have ridden scooters in the past. It's a lot of fun. Well, he runs one of the scooter companies, and he's building autonomous control onto some of the scooters so they can automatically like reposition themselves on the sidewalk out of people's way, maybe go to a charging station, things like that. So he'll bring that. It'll be for after lecture. If you're interested, make sure you allocate a little bit of time after lecture so you can see that in action, talk with him, and learn more about some kind of practical autonomy that's being built. All right, see you on Thursday.
Station.